Somewhere just behind your eyes, right now, something is happening that you did not ask for and cannot turn off. Light is landing. It has been traveling, some of it, for 8 minutes from a star 93 million miles away, and some of it has only traveled a few feet, bouncing off a wall or a blanket or the inside of your own eyelids, and all of that light, old and young, distant and near, is arriving at two small curved surfaces on the front of your head and bending inward, and coming to rest on a thin layer of tissue about as thick as a few sheets of paper, and there, in that thin layer, something is quietly catching fire. Not literally, but close enough as a metaphor to sit with for a moment. Photons, tiny packets of electromagnetic energy, are striking specialized cells, and those cells are changing shape in response, and that shape change is triggering an electrical signal, and that signal is heading backward into your skull, toward a part of your brain that has never once, in your entire life, directly touched the outside world. This is happening to you right now, whether your eyes are open or closed, whether the room is bright or dim, whether you are paying attention to any of it or not. It is one of the most constant facts of being a sighted creature, and it is also, if you slow down and really look at it, deeply strange, because somewhere in that chain of events, between the photon and the feeling, something gets added. The photon itself has no color. It has a wavelength, a measurable physical property, a certain number of nanometers from crest to crest. But wavelength is not color, not exactly, not yet. Color is what happens after. Color is the brain's response to the wavelength, not the wavelength itself. And that gap, that small, quiet gap between the physical world and the felt world, is where this entire subject lives. I want to start there, in that gap, because it is the thing that makes color so quietly confusing for almost everyone, even people who have thought about it for years. We grow up believing, without ever really examining the belief, that color belongs to things. The sky is blue, grass is green, a stop sign is red. These feel like facts about the world, in the same way that a rock is hard or water is wet. But hardness and wetness are at least partly measurable, using tools that do not involve a nervous system. You can press a rock with a machine and get a number. Color does not work quite like that. There is no colorimeter you can point at an apple that will return the answer red in the way a thermometer returns a temperature, because red is not out there in the apple waiting to be detected. Red is something that happens inside you, assembled from information the apple's surface happens to send outward. This is not a small philosophical footnote. It is closer to the load-bearing wall of the whole topic, so let it settle for a moment. The apple's skin is covered in molecules called pigments, and those pigments have a particular habit, which is that they absorb some wavelengths of light and reflect others. A ripe apple's skin tends to absorb most of the shorter wavelengths, the ones we would call blue and green, and reflect back a good deal of the longer wavelengths, the ones we would call red. That reflected light travels to your eye, gets caught by those light-sensitive cells, and gets converted into signals that eventually produce, somewhere in your visual cortex, the experience you know as redness. But notice what the apple itself is doing in all of this. It is not producing red. It is subtracting. It is absorbing certain wavelengths and letting others bounce away. The apple, in a strange sense, is not red so much as it is everything except red, or more precisely, it is a surface that declines to keep the red wavelengths for itself and sends them back out into the world,
where your eyes happen to be waiting. If that sounds like a small technicality, consider what it means for the color you experience. It means the redness you feel when you look at that apple is not a copy of some redness sitting inside the fruit. It is your nervous system's interpretation of a pattern of reflected light, built according to rules that evolved inside animal brains over hundreds of millions of years, rules that have almost nothing to do with the apple and everything to do with you. Two people can stand next to each other, looking at the same apple, bathed in the same light, and have what are almost certainly, in some deep and unverifiable way, different inner experiences of red, even while agreeing completely on the word they would use to describe it. This is one of the oldest puzzles in the study of the mind, sometimes called the problem of qualia, and it tends to keep philosophers up at night, though hopefully it will do the opposite for you. It might help to picture the whole system as a kind of translation chain, several links long, each one changing the message a little. At one end of the chain is the physical world, full of surfaces and light sources and molecules, none of which have any color in them at all, only tendencies to absorb and reflect particular wavelengths. In the middle of the chain are your eyes, converting physical light into electrical patterns, a translation from photons into nerve impulses. And at the far end of the chain is your brain, taking those electrical patterns and constructing, out of them, a rich inner experience of hue and brightness and saturation. An experience that feels immediate and effortless, and located out there in the world, even though it was built, piece by piece, entirely in here. By the time you consciously see the color of anything, several translations have already happened, invisibly and instantly, and you are left holding only the final result, with no memory of the steps that produced it. This is worth pausing on, because it explains a kind of vertigo that some people feel the first time they really absorb it. If color is not a property of objects, then in what sense is the world colorful at all? The honest answer, and it is not meant to be unsettling, only clarifying, is that the world is colorful, in exactly the sense that it is home to creatures capable of experiencing color, and not really, in any other sense that survives close inspection. A world with no eyes in it, no brains, no nervous systems of any kind, would still have all the physics. Light would still bounce and scatter, and split into different wavelengths. But there would be no red, anywhere in that world, no blue, no green, only electromagnetic radiation of varying frequencies, doing what electromagnetic radiation does, indifferent to any of it. Color, in this sense, is less like a substance sitting in the world, waiting to be found, and more like a kind of music that only plays when the right instrument is present to play it on. None of this means color is somehow fake, or that your experience of a sunset, or a garden, is an illusion in the dismissive sense of that word. It means something gentler, and, in its own way, more remarkable. It means that color is a genuine collaboration between the physical world and a living nervous system, something that neither one could produce alone. The apple contributes its particular pattern of reflectance, shaped over generations of selective breeding, by farmers who themselves were choosing for a certain shade of red, without necessarily knowing anything about wavelengths. And your visual system contributes the rest, an elaborate inherited machinery, built by evolution to notice differences in reflected light, because those differences, across millions of years, correlated with things that mattered: ripe fruit against green leaves, a flushed face, a change in the sky before a storm. Color is the meeting point of those two histories, one written in chemistry and physics, the other written in biology and time. So as you lie here, with light still landing quietly on the backs of your eyes even in a dim room, It might be worth simply noticing that a construction is underway. Somewhere behind your closed or half-closed eyelids, patterns are being caught, translated, and reassembled into something that feels like a picture of the world, complete with colors that seem to belong to the things themselves. That feeling, that seamless sense of color living out there on the surface of objects, is itself one of the most persuasive illusions the brain produces. Not because it is trying to deceive you, but because it is doing its job so well that the seams disappear entirely. And once you start noticing those hidden seams, even just a little, it becomes easier to understand why something as ordinary as the color of an apple, or a wall, or a stretch of evening sky, turns out to rest on a question that took scientists a very long time, and a great deal of careful, patient argument, to even learn how to ask properly.
Let's slow down and go back, further than the apple, further than the eye, to something even quieter and even stranger. Let's talk about light itself, before it ever reaches a leaf or a face or a window. Because before we can understand what your nervous system is doing with light, it helps to understand what light is actually doing, out there, in the dark, traveling. Light is a kind of wave, not a wave in water, not a wave you could ride or feel against your skin, but a wave in something more abstract, an oscillation in electric and magnetic fields, rippling together through space, each one regenerating the other as it goes. This is why physicists call it electromagnetic radiation, a phrase that sounds clinical and a little cold, but which describes something that has been rippling through the universe since long before there were eyes anywhere to notice it. Long before the first eye opened on this planet, light was already crossing empty space, already bouncing off rock and water and dust, utterly indifferent to whether anything was there to receive it. You can picture these waves, if it helps, the way you might picture ripples spreading across a still pond after a stone drops in. Some ripples are close together, rising and falling quickly, one after another. Others are spread further apart, rising and falling in slower, longer stretches. The distance between one peak and the next is called a wavelength, and it turns out that this single measurement, the spacing between peaks, is almost everything. It is the detail that separates radio waves, which can be kilometers long, from the light your eyes are built to notice, which is almost inconceivably smaller, measured not in meters, but in nanometers, billionths of a meter, distances so small that a single human hair is many hundreds of times wider than one wavelength of visible light. The full range of electromagnetic waves is vast, almost uncomfortably vast to imagine all at once. At one end, you have radio waves, long and slow, used to carry music into a car on a late drive home. Then microwaves, then infrared, which you cannot see, but which you have certainly felt, as the warmth radiating from a fire or from sun-warmed pavement. Then, tucked into a narrow band, right in the middle of this enormous spectrum, comes something almost startling in its narrowness. A sliver of wavelengths, running roughly from about 400 nanometers to about 700 nanometers, which is the entire range of electromagnetic radiation that human eyes are built to detect. Beyond that sliver, in one direction, lies ultraviolet, then X-rays, then gamma rays, shorter and shorter, more and more energetic. In the other direction, past infrared, lie microwaves and radio waves, longer and longer, gentler and gentler in their energy. Almost the whole spectrum, in other words, is dark to us. Not dark in the ordinary sense, not black or empty, but simply unseen,
silent to the particular instruments sitting inside your skull.
We have built machines that can detect these other wavelengths. Radios, X-ray scanners, infrared cameras that can find a warm body in a cold building. But our eyes themselves were never built for any of that. They were built for this one narrow ribbon, and for reasons that made sense for a creature standing under a particular kind of star. That ribbon of wavelengths we can see is what scientists call visible light, and it is worth sitting with how strange it is that we call it visible at all, as though visibility were a property of the light itself, rather than a property of the relationship between that light and a particular kind of eye. To a creature with different eyes, a bee, say, or a mantis shrimp, the visible range would be drawn differently, would include ultraviolet patterns on flowers invisible to us, would perhaps divide the world into a wholly different set of narrow bands. Visible is not a fact about the universe. It is a fact about us, about the particular sliver of electromagnetic radiation that happens to trigger the particular molecules sitting in the backs of our eyes. Now, there is another way to describe this same light, a way that physicists sometimes reach for instead of the wave picture, and it is worth mentioning gently here because it will matter later. Light can also be described as a stream of small packets of energy called photons. This is not a contradiction of the wave description, though it can feel like one at first, lying here trying to picture it. It is more that light seems to behave, depending on how you look at it, sometimes like a wave spreading and rippling through space, and sometimes like a stream of discrete little bundles, each one carrying a specific, quantized amount of energy. Physicists spent a long time, well into the early 20th century, arguing and experimenting their way toward accepting that both descriptions were somehow true, or at least both useful, each one capturing something real that the other missed. You do not need to resolve that puzzle tonight. It is enough to know that a photon's energy relates directly back to that same idea of wavelength, shorter wavelengths carrying more energy per photon, longer wavelengths carrying less, so that the two pictures, wave and particle, stay connected underneath, describing the same underlying reality from two different angles. So light arrives, whether we picture it as ripples or as photons, streaming outward from the sun, or from a candle, or from the warm glow of a lamp beside a bed, and it travels until it meets something solid. And this is where the story starts to become more interesting, because what happens next depends enormously on what that something is made of. Every surface you have ever touched is built from atoms and molecules, arranged into particular structures, and those structures interact with incoming light in very specific ways. Some wavelengths of light, hitting a given surface, get absorbed, which means their energy is taken up by the electrons in the material, converted into heat or into some other form of internal energy, and simply does not bounce back out again. Other wavelengths, hitting that same surface, are not absorbed at all. Instead, they bounce, or more precisely, they are reflected, scattering back off the surface and out into the world, continuing their journey in a new direction, potentially straight toward your eye. This is the whole secret, sitting underneath the color of things, though we have not yet arrived at color itself, only at its raw material. A surface that we will eventually call red is a surface that happens to absorb most of the shorter wavelengths of visible light, the ones we will later associate with blue and green, while reflecting back a good portion of the longer wavelengths, the ones we will later associate with red. A leaf that we call green is doing something similar but shifted, absorbing red and blue wavelengths for use in photosynthesis, while reflecting green back outward, almost as a kind of leftover,
and excess the plant had no particular use for. Nothing about this process, at the level of atoms and reflected wavelengths, involves redness or greenness in any experiential sense. It is simply a pattern, a particular fingerprint of which wavelengths bounce away and which get absorbed, different for every material, for every pigment, for every surface you have ever looked at without thinking twice about it. And here is the quiet, important distinction, worth letting settle before sleep pulls you further under. What arrives at your eye, in this picture, is only ever a mixture of wavelengths, a physical pattern of electromagnetic radiation bouncing off a surface, carrying no color within it, not yet. The light itself is not red or green or blue. It is simply energy, oscillating at certain frequencies, in certain proportions, entirely colorless, in the way that a number is colorless, or a rhythm is colorless, present and measurable and real, but not yet transformed into any experience at all. That transformation, the moment where a physical pattern of reflected wavelengths becomes something felt, something that seems to glow, or warm, or soothe, has not happened yet in this part of the story. It is still waiting, further down the path that light takes, at the surface of the eye itself, where this quiet stream of wavelengths is about to meet something that can finally begin to read it. Let that stream of wavelengths keep traveling for a moment, because it has a short journey left before it meets anything capable of reading it. It passes first through the cornea, the clear dome at the very front of the eye, curved like the surface of a watch glass, and this curve is not decorative. The cornea bends light as it enters, doing more of the actual focusing work than most people assume, more even than the lens sitting just behind it. You can think of it as the first and roughest adjustment, a wide, general bending of the incoming rays toward a single point somewhere deep inside the eye, the way a hand might rough out the shape of clay before finer tools ever touch it. Behind the cornea is a small chamber filled with a clear fluid, and behind that the iris, the ring of color you see when you look into someone's eyes up close, though of course we are getting ahead of ourselves by even calling it colored, since we have not yet reached the part of the story where color exists. Still, it is worth noticing that the iris is a muscle, a drawstring of tissue that opens and closes the pupil at its center, widening in dim rooms to let in more of the sparse light available, narrowing in bright sunlight to keep from flooding the more delicate structures further back. This is not so different from the aperture of an old camera adjusting itself to the available light, though the iris does this constantly, without instruction, a reflex so old it predates almost everything else we will talk about tonight. Light that makes it through the pupil, then reaches the lens, a soft, flexible structure that fine-tunes the focus the cornea began. Muscles around the lens can pull it thinner or let it plump rounder, changing how sharply the light converges, which is how your eye manages to focus on a page held close, and then, a moment later, on something far across a room, without you ever having to think about the adjustment. This flexibility fades with age, gradually, which is why reading glasses tend to arrive in a person's 40s or 50s, not because the eye stops working, but because the lens stops being able to change its shape as readily as it once did. Johannes Kepler was among the first to describe this optical arrangement correctly, back in the early 1600s, working out that the eye functions something like a camera obscura, projecting an image onto a surface at the back, though it would take a little longer for anyone to fully understand what happens once that image lands. Because that is really the heart of where we are heading now. All of this bending and focusing exists for one purpose: to take the scattered, colorless wavelengths reflecting off the world, and concentrate them into a sharp, small image on the back inner wall of the eye, a curved surface called the retina. And it is here, finally, after all this quiet architecture of cornea and pupil and lens, that something genuinely strange begins to happen. The retina is not simply a screen, the way film in an old camera was a screen, passively holding an image. It is a thin, living sheet of tissue, only about 1/4 of a millimeter thick in most places, and packed into that thinness are the cells that will do the actual work of converting light into something the brain can use. This is the boundary we have been walking toward. On one side of it, still, wavelengths. On the other side, beginning just a few thin layers of tissue away, something closer to meaning. The retina holds 2 broad families of light-sensitive cells, named for their shapes under a microscope. Long ago, by people squinting through early lenses at tissue that had been stained and sliced impossibly thin. Rods are the more numerous of the two, numbering somewhere around 90 to 120 million in a typical human eye, and they are extraordinarily sensitive to light, capable of responding to a single photon under the right conditions, which is a sensitivity almost hard to picture, given how little that actually is. But rods pay for this sensitivity with a kind of color blindness. They come in only one variety, tuned roughly to the same range of wavelengths, which means that on their own, rods cannot distinguish one wavelength from another at all. This is part of why the world seems to lose its color in very dim light, at dusk, in a moonlit room, in the deep blue hour just before true dark. It is not that color disappears from the light itself. It is that the rods, which take over the job of seeing once light grows too scarce for anything else, are simply not built to report which wavelengths are present, only that light is present at all. Cones are the other family, and there are far fewer of them, something like 6 million scattered across the retina, concentrated most densely in a small central pit called the fovea, the spot you use whenever you look directly at something to bring it into sharp focus. Cones need considerably more light to function well than rods do, which is why fine detail and rich color both tend to fade together in dim settings, both depending on this same smaller, hungrier population of cells. But cones offer something rods cannot, because most humans possess not one kind of cone, but 3, each tuned to respond most strongly to a different range of wavelengths, though tuned is perhaps too tidy a word for what is actually a wide, overlapping, imprecise kind of sensitivity. It helps to picture these 3 cone types, not as narrow specialists, each locked onto a single wavelength, like a key fitting one lock, but as broad, overlapping listeners, each one responsive across a wide swath of the visible spectrum, just leaning more strongly toward one region than the others. One type of cone responds most vigorously to shorter wavelengths, the region we will eventually call blue, though even here, the response curve is broad, catching a great deal of violet and a fair amount of green along the way. A second type responds most strongly toward the middle of the visible range, in the area we will eventually call green, though its curve stretches out generously into yellow and even orange territory. A third responds most strongly toward longer wavelengths, the region eventually called red, though its curve too drifts backward into orange and yellow, overlapping substantially with the middle cone's territory. In fact, the overlap between these last two cone types is so extensive that their response curves sit almost on top of each other, for a wide stretch of the spectrum, differing mostly in degree rather than in kind. This overlapping is not a flaw in the design, even though it might sound at first like something blurry or imprecise. It is, in a strange way, the entire secret of how color vision works at all. Because a single cone, all by itself, cannot tell you what wavelength of light has struck it. A cone firing more strongly could mean it received a great deal of dim light near its peak sensitivity, or a lesser amount of light at a wavelength it happens to respond to especially well. One firing rate, considered alone, is hopelessly ambiguous, carrying no wavelength information on its own at all. What allows the system to work is comparison. The brain does not read any one cone's signal in isolation. It reads the relationship between all three signals at once. The particular ratio of how strongly the short, middle and long sensitive cones are each responding to the same patch of light, and it is that ratio, that pattern of relative activation across three overlapping but distinct populations, which becomes the raw code from which color experience will eventually be built. This is part of why three cone types, despite seeming like such a small number, can support the vast range of color experiences most people report, something often estimated in the millions of distinguishable shades, though that figure depends heavily on how you test for it, and what counts as a meaningfully different color at all. Three overlapping curves, compared against each other in shifting ratios, can produce an enormous number of distinguishable combinations. In something like the way three overlapping colored lights, angled just right, can paint a wall in far more shades than three alone would suggest. And it is this comparison, this quiet arithmetic of ratios happening in cells no wider than a few microns, that we will need to follow further, into the layers just behind the cones themselves, where the signal begins its long relay toward the brain.
Let's follow that ratio, that quiet comparison of three overlapping signals, just a little further back into the eye, into the layer of cells, sitting immediately behind the cones themselves. This is where something rather surprising happens, something that took the science of vision a long time to fully accept. You might expect that the eye would simply pass along three separate streams of information, one for each cone type, like three messengers, each carrying their own letter to the brain. But that is not quite what happens. Almost immediately, the raw cone signals are recombined, subtracted from one another, compared and recompared, so that by the time information leaves the eye along the optic nerve, it is no longer traveling as three independent cone reports at all. It has already been converted into something else, a smaller set of coded differences, and this recoding is called opponent processing. The idea has a long and slightly tangled history. In the late 19th century, a German physiologist named Ewald Hering noticed something that seemed hard to reconcile with the three-color theory that was already gaining acceptance in his time, largely through the work of Hermann von Helmholtz. Hering pointed out that certain color combinations simply do not seem to exist in ordinary experience. People can easily imagine a reddish-orange, or a yellowish-green, or a bluish-purple, but almost no one, when asked to picture it, can conjure a reddish-green or a yellowish-blue. Try it for a moment, lying there in the dark. Try to picture a color that is both red and green at once, not a mixture that looks brownish or muddy, but a single hue that feels like pure red and pure green blended together the way orange feels like a blend of red and yellow. Most people find the request strange, almost meaningless, as though they have been asked to imagine a sound that is simultaneously silent. For Wien took this seriously, and he proposed that the visual system might be organized not around three independent color channels, but around paired opposites, where red and green sit at two ends of a single dimension, and blue and yellow sit at two ends of another. For decades, Hering's opponent theory and Helmholtz's trichromatic theory were treated as rivals, as though only one of them could be correct. It turned out, once physiologists in the middle of the 20th century began recording directly from cells behind the retina, that both men had been describing real things, just at different stages of the same process. Helmholtz was right about the cones themselves, the three overlapping types of receptor, sensitive to short, medium, and long wavelengths, and Hering was right about what happens next, because almost immediately after the cones fire, their signals get wired together in a way that produces exactly the kind of opposing pairs he had guessed at from pure introspection, without ever seeing a single nerve cell. Here is roughly how the wiring works, described in a simplified way that keeps the shape of the truth without drowning in anatomical detail. Certain cells just behind the receptors take the signal from long wavelength cones, the ones most excited by light we would call reddish, and set it against the signal from medium wavelength cones, the ones most excited by light we would call greenish. The cell does not report both signals separately, it reports their difference. If the long wavelength signal is stronger, the cell pushes its output in one direction, toward what will eventually be experienced as redness. If the medium wavelength signal is stronger, the cell pushes its output the other way, toward greenness. And if the two signals happen to be closely matched, balanced against each other, the cell settles near a neutral point, contributing neither strong red nor strong green to the eventual picture. A useful way to hold this in mind, as you drift, is to think of a simple balance scale, the old-fashioned kind with two pans hanging from a beam. On one side sits the weight of the long wavelength cone signal, on the other side sits the weight of the medium wavelength cone signal. The beam does not care how heavy either side is in absolute terms, it only cares which side is heavier, and by how much. A very bright reddish light and a very dim reddish light can tip the beam by roughly the same amount, so long as the ratio between the two cone signals is similar, because the cell is reporting a comparison, not a raw quantity. This is part of why a red apple looks red to you, whether it is sitting in bright sunlight or in the dimmer light of a lamp, even though the actual number of photons reaching your eye has changed enormously between those two situations. The comparison, the ratio, stays relatively stable even as the absolute brightness swings. A second opponent channel handles blue against yellow, though this one is built a little differently, because there is no single cone type that responds best to yellow light the way there is for blue. Instead, the short wavelength cones, the ones tuned toward blue, are compared against a combined signal from both the medium and long wavelength cones added together, since a mixture of medium and long wavelength activity is what tends to accompany yellowish light. Picture, if it helps, a second balance scale standing beside the first one. On one pan sits the short wavelength cone signal, representing blue. On the other pan sits the combined weight of the medium and long wavelength signals working together, representing yellow. Again, the beam tips one way or the other, depending on which side carries more weight, and that tip becomes the raw material for the sensation of blueness or yellowness. There is a third channel running alongside these two.
one that does not compare colors against each other at all, but instead adds the cone signals together rather than subtracting them, producing a running measure of overall brightness, sometimes called the luminance channel, or described more simply as a brightness or black-white channel, where the red-green and blue-yellow channels are built from subtraction, from difference. This third channel is built more from summation, a rough total of how much light is landing on a given patch of retina, regardless of its particular color.
It is this channel that tends to carry the sharpest, most detailed spatial information, the fine edges and textures of a scene, while the two color opponent channels tend to carry information at a somewhat coarser resolution. This is part of why, if you have ever noticed it, a pattern made only from a barely perceptible color change, red dots on a red background of only slightly different redness, can be nearly invisible from a distance, while the same pattern made from a brightness change, gray on white, remains sharp and legible from much farther away. Your visual system has, in effect, dedicated more of its fine spatial resolution to brightness than to color, a compromise our species has lived with without much noticing. Something else worth sitting with, in this same neighborhood of the visual system, is how strongly this whole arrangement depends on edges and boundaries rather than on the color of any single point in isolation. The cells doing this opponent comparison work are typically organized in a pattern with a center and a surround, a small central region compared against a ring around it. A cell might be excited by reddish light landing on its center while being suppressed by reddish light landing on its surrounding ring, or the reverse. This means these cells are, in a real sense, built to detect contrast and change, built to notice where one color or brightness meets another, rather than to simply register a flat, uniform patch of light sitting quietly by itself. A perfectly even field of one unchanging color, with no edges anywhere in it, tends to fade from vivid awareness rather quickly, the way a hand resting motionless on your arm eventually seems to disappear from feeling altogether. Vision, at this level, is not really built to report what is there in some absolute sense. It is built to report what is different from what surrounds it, moment to moment, edge to edge. So, by the time signals leave the eye and travel along the optic nerve toward the brain, they have already been transformed twice over. First, 3 overlapping cone types converted incoming light into 3 ratios of activation. Then, almost immediately, a layer of comparison cells recoded those 3 ratios into a smaller set of opposing signals: red, measured against green, blue, measured against yellow, and brightness, measured as a rough sum, all of it organized around detecting edges and contrasts rather than flat, isolated colors. None of this, notably, has produced anything you would call an experience yet. There is no redness here in any way a philosopher would recognize, no felt quality, nothing it is like to be this pattern of firing. What exists, at this stage, is only a code, a set of differences traveling along a bundle of nerve fibers no thicker than a shoelace, heading toward a destination deep inside the skull, where, somehow, out of pure electrical pattern, something like the feeling of color is eventually going to arise, and it is toward that destination, into the brain itself, that we can now let our attention drift. Take a moment, before we go any further, to picture something almost embarrassingly ordinary. A white shirt, hanging on a chair in a bedroom. In the morning, sunlight comes through the window at a low angle, tinted faintly orange, the way light gets when it has traveled through a thicker slice of atmosphere. Later, at noon, the light turns closer to a neutral blue-white. In the evening, a lamp switches on, and the bulb inside it, if it is an old-fashioned incandescent one, bathes the room in a warm yellow-orange glow. Measure the actual wavelengths of light bouncing off that shirt at each of these 3 moments, and you would find genuinely different mixtures arriving at your eye. Morning light skews the reflected spectrum toward orange. Noon light leaves it closer to balanced. Evening lamplight skews it toward yellow again, sometimes even more strongly than the sunrise did. And yet, through all of this, you would say, without hesitation, that the shirt is white. Not whitish in the morning, and a different white at noon, and slightly yellowed by lamplight. Just white, stable, unchanging, the whole day through. This is strange, if you stop to really examine it. Your eyes are being fed different information at every hour, and your experience refuses to follow along. Something in the visual system is quietly discounting the light itself, treating the illumination as a variable to be subtracted out, so that what remains looks like a fixed property of the object. This is called color constancy, and it turns out to be one of the more remarkable feats your brain performs without ever mentioning it to you. Consider how strange this would sound if a similar trick happened with sound. Imagine if a voice, heard first in a quiet room and then again through a wall, or first close up and then from far away, seemed to change identity each time the acoustics shifted, so that you could no longer recognize your own name spoken by someone familiar unless the room stayed exactly the same. That would make the auditory world nearly impossible to navigate. Vision faces exactly this problem and mostly solves it, which is why you can walk from a fluorescent-lit office into afternoon daylight, into a candle-lit dinner, and still recognize a red apple as red, a green apple as green, throughout. The raw wavelengths bouncing off that apple change substantially between those 3 settings. Your judgment of its color barely changes at all. How does the brain manage this? Part of the answer lies in something we touched on earlier, that opponent cells and retinal circuits are wired to respond to contrast and ratios rather than to absolute quantities of light. If every surface in a room is being lit by the same orange-tinted morning sun, then every surface has its reflected light shifted toward orange by roughly the same amount. A white shirt gets shifted, but so does a gray blanket beside it, and so does the pale wood of the floor. The visual system, in a rough and imperfect way, can compare surfaces against each other, note that the overall cast is uniformly warm, and essentially subtract that shared warmth back out, the way you might notice that every photograph from an old camera has a slight yellow tint, and mentally correct for it while looking at a whole album, rather than judging each photograph in isolation. The brain seems to be doing something like this constantly, estimating the color of the light source itself, almost as a background calculation, and using that estimate to reinterpret everything lit by it. There is a 19th century thread to this story, worth pausing on. The physicist and physician Hermann von Helmholtz, working in Germany in the 1860s, proposed that a great deal of perception involves what he called unconscious inference, meaning the brain does not simply record raw sensory data, but actively interprets it, drawing on assumptions built from a lifetime of prior experience, without ever letting that interpretive work reach conscious awareness. Applied to color, this idea suggests that when you look at the white shirt under evening lamplight, your visual system is not passively reporting the yellowish light bouncing off the fabric. It is running a kind of implicit calculation, something like, given how yellow this whole room appears to be, and given how yellow the light source itself seems to be,
What would this surface's color be if it were lit by something closer to neutral daylight instead? And the answer that calculation returns is white, because the shirt would indeed look white under daylight, and the room's general yellow cast gets attributed to the lamp rather than to the shirt itself. None of this happens as a conscious chain of reasoning, of course. Nobody sits in their bedroom deliberately calculating the color temperature of their lamp before deciding their shirt is white. The inference, if that is even the right word for it, happens instantly, silently, somewhere beneath the threshold of anything you could describe as thought. Shadows offer another angle on the same puzzle, and a particularly vivid one. Picture a checkerboard floor in direct sunlight, half of it lying in the sharp shadow cast by a nearby wall. The dark squares sitting in full sun, and the light squares sitting inside the shadow, can, under the right conditions, reflect nearly identical amounts of light back to your eye. Measured with an instrument, they might be almost indistinguishable, and yet no one looking at that floor would say the shadowed light square looks as dark as the sunlit dark square. Your visual system takes the presence of a shadow into account, essentially reasoning that a square appearing dim inside a shadow is probably a light-colored square that simply has less light falling on it, while a square appearing dim in full sunlight is probably an intrinsically dark square. This is the same discounting process at work again, treating the pattern of illumination across a scene as information to be factored out, so that what survives in your perception is something closer to the object's actual reflectance, its stable, physical tendency to reflect certain wavelengths, independent of how much or what kind of light happens to be falling on it in a given instant. This is, incidentally, part of why certain optical illusions involving shadows in checkerboards feel so unsettling the first time someone encounters them, sometimes described using a famous example designed by the vision researcher Edward Adelson in the 1990s, in which two squares on a checkerboard, one inside a cast shadow and one outside it, appear to be strikingly different shades of gray, even though, measured directly, they are printed with the exact same value of gray ink.
Cover the rest of the image so only those two squares remain visible, with no shadow, no surrounding checkerboard pattern, no context at all, and they suddenly look identical, because the shadow discounting machinery has nothing left to work with. It is a small, almost eerie demonstration of just how much interpretive work is happening beneath the surface of something as apparently simple as looking at a floor. Dawn and dusk push this whole system toward its limits, because at those hours, the tint of the light is shifting continuously and dramatically, sometimes over the span of only a few minutes. Sunlight scattered through a thick layer of atmosphere near the horizon loses much of its blue content, since blue wavelengths scatter more easily than red and orange ones, a phenomenon governed by the same physics that makes the daytime sky blue in the first place. This is why the sky itself glows orange and pink at these hours, and why anything lit by that sky, a wall, a cloud, the side of a mountain, briefly takes on those same warm tones. A skilled painter, someone trained to notice color rather than simply infer it, will tell you that shadows at sunset often appear distinctly blue or violet, not gray, because they are being lit not by the warm, direct, dying sunlight, but by the cooler, bluer light scattered down from the rest of the open sky. Most people never consciously register this. Their visual system quietly discounts the overall warm cast of the whole sunset scene, so a white wall, lit by dusk light, still reads as roughly white to them, even while, if you ask them to look very carefully and describe only the shadows in isolation, they might suddenly notice a blue tinge they had somehow missed the whole time. The color was there,
in the light the entire time. Noticing it consciously turns out to require a strange kind of deliberate unlearning, a temporary switching off of the very machinery that ordinarily keeps your perceived world so reassuringly stable.
Let's think, for a while, about a butterfly wing and a bottle of paint, both blue, and ask what they actually have in common. The honest answer is almost nothing, physically. This turns out to be one of the stranger facts about color, and a good one to drift through slowly, because it quietly rearranges what blue even means. Start with the paint, since it is the more intuitive case. A tube of blue paint contains countless tiny particles, pigment, suspended in some binding medium, oil or acrylic or egg yolk if you are working the way painters did centuries ago. Each particle has a molecular structure that absorbs certain wavelengths of light and lets others go. Ultramarine, the intense blue ground for centuries from lapis lazuli, mined in the mountains of what is now Afghanistan, absorbs red and yellow light and reflects blue back toward your eye. This pigment was once so costly, rarer than gold by weight, that Renaissance painters reserved it specifically for the robes of the Virgin Mary, a single color standing in for devotion and expense at once. The physics underneath that reverence is simple absorption. Light goes in, certain wavelengths are captured by the electron structure of the molecule and converted to a small amount of heat, and the rest bounces back out. What you see as blue is really the leftover, the wavelengths the pigment did not want. Dyes work on a closely related principle, though the mechanics differ slightly from pigments. A dye actually bonds at the molecular level with the fibers it colors, sinking into cloth or thread, rather than sitting on top of it as discrete particles, the way pigment does in paint. This is why dyed fabric can survive years of washing, while a poorly bound pigment coating flakes and fades. Indigo, used for thousands of years to color cloth, from ancient Egyptian burial wrappings to the blue jeans humming along on countless legs today, absorbs light in almost the same selective way ultramarine does. Different molecule, different chemistry, same basic principle, certain wavelengths absorbed, certain wavelengths sent back out toward whatever eye happens to be nearby. Now leave the paint and the dye behind entirely and go stand next to a morpho butterfly, one of those brilliant iridescent blue insects found in Central and South America, the kind whose wings seem almost too saturated to be real, glowing with a blue that shifts and shimmers as the insect moves. Grind up a morpho wing, and you get gray dust, not blue dust, gray. This single fact undid a great deal of confused 19th century speculation about butterfly pigmentation, because it turns out there is no blue pigment there at all to grind up. The color is not a substance. It is a shape. The wing scales of a morpho butterfly are structured in extraordinarily fine, repeating layers, ridges and lattices built at a scale close to the wavelength of visible light itself, thinner than anything a human hand could carve. When light strikes these structures, it does not get selectively absorbed the way it does in pigment. Instead, it gets reflected off multiple tiny surfaces at once, and those reflected waves interfere with each other, some canceling out, some reinforcing, in a way that happens to reinforce blue wavelengths specifically, while canceling most others. This is called structural color, and it is a genuinely different physical mechanism from pigment color, even though both can produce something your visual system files under the same word, blue.
One is chemistry, the other is architecture. This is worth sitting with for a moment, because it explains something that puzzles people the first time they hear it. Why structural blues tend to shimmer and shift with angle, growing greener or darker or almost black, depending on exactly how the light hits them and exactly where your eye is standing, while a wall painted with blue pigment looks basically the same blue, no matter where you walk around the room. Pigment color is fairly stable because it depends on the molecule's structure, which does not change as you move your head. Structural color depends on geometry relative to the light source and the viewer, so it is inherently unstable, in the sense of shifting rather than staying fixed, catching light differently from every angle, the way the surface of a soap bubble does, or the inside of an abalone shell, or the sheen on a starling's feathers, black in some light, and suddenly a deep glossy green-purple in others. Peacock feathers work this way too, structural, rather than pigmented, which is part of why they seem to glow, rather than simply sit there being colored. There is a third mechanism worth mentioning here, closely related to structural color, but distinct enough to deserve its own quiet moment of attention, and that is scattering, the phenomenon already mentioned in passing when thinking about the blue of the sky itself. Scattering happens when light bounces off particles or structures that are small compared to its wavelength, and it bounces unevenly, favoring shorter blue wavelengths over longer red ones. This is why the sky is blue during the day, and why smoke from a distant fire, viewed against a dark background, often looks faintly blue itself. Its tiny particles scattering short wavelengths, preferentially, before any color has been added or subtracted by absorption. Some blue eyes work by an almost identical logic. There is no blue pigment in a blue iris. Instead, there is a layer of tissue containing tiny structures that scatter light much the way the sky does, on a much smaller and much closer stage, tucked inside someone's eye rather than stretched across the upper atmosphere. This is a small, strange fact people sometimes find unsettling the first time they learn it, that the blue of someone's eyes is, mechanistically, a cousin of the blue of the sky, both born from scattering, rather than any dye or pigment doing the coloring. And then there is a fourth path entirely, stranger still, called fluorescence, worth mentioning briefly here, even though its full richness deserves more room than a passing note. Certain materials absorb light at one wavelength, often light your eyes cannot even see, ultraviolet, and then re-emit it, almost instantly, at a different, longer wavelength that you can see, glowing with a color that seems to come from nowhere, seems almost to generate its own light, rather than merely reflecting what fell on it. Some corals do this. Some minerals do this, famously turning dull gray rock into brilliant glowing green, or orange, under an ultraviolet lamp in a darkened room. Certain laundry detergents include fluorescent brighteners for exactly this reason, absorbing invisible ultraviolet light from the sun and re-emitting it as visible blue light, which makes white fabric look not just clean, but almost supernaturally bright, whiter than white, a small optical trick built into nearly every box of detergent on the shelf. Now bring the fourth kind of blue back into the room, the screen. A phone or television screen makes blue an entirely different way again, not through pigment, not through structural interference, not through scattering, not through fluorescence in the usual sense, but through emission. Tiny elements built directly into the display, historically phosphors excited by an electron beam in the old cathode ray tube sets, and in modern screens, light-emitting diodes or liquid crystal filters gating a backlight, producing light of a specific wavelength directly, rather than reflecting or filtering light that arrived from somewhere else. A screen does not wait for ambient light to strike it, and then subtract some wavelengths, the way a painted wall does. It generates its own blue outward, into the room, which is part of why screens remain visible in the dark, while a blue painted wall, in the same dark room, disappears into blackness, having nothing left to reflect. So here is the strange, quiet unity, underneath all this apparent variety. A butterfly wing, a square of ultramarine paint, a pair of blue eyes, a patch of denim, a stretch of afternoon sky, and a glowing phone screen, can all produce something your visual system calls blue. And yet the physical route each one takes to get there is almost completely different. Absorption and reflection in the paint, molecular bonding, and absorption in the dye, nanoscale interference in the wing, scattering in the sky, and the iris, an absorb and remit trick in fluorescence, and direct emission in the screen. Your eyes and your visual cortex do not know, and do not care, which of these physical stories produced the light now landing on your retina. They only register the wavelength composition of that light, and translate it into the single, seemingly effortless experience of a color. Which raises a question, worth carrying gently, into the next stretch of this drift toward sleep. If the machinery producing blue light is this varied out in the world, what exactly is happening inside the eye itself that manages to receive all of these different physical signals and quietly, wordlessly, sort them into the same simple sensation?
Now, before we drift into the eye itself, let's linger a little longer out here in the world of light, because there's a particular puzzle in how colors combine that trips people up for years, and untangling it slowly, right before sleep, tends to make it stick in a calmer, more permanent way than any daytime explanation usually manages. Here is the puzzle. If you mix blue and yellow paint, you get green. Most people learn this before they learn to read, dabbling in kindergarten with a paintbrush and a paper plate serving as a palette. But if you mix blue and yellow light on a screen or in a theater, you don't get green at all. You get something close to white, or a pale, washed-out gray, depending on the exact wavelengths involved. This seems like a contradiction, the kind of small, unresolved itch that can needle at a person for years without ever getting scratched. It isn't a contradiction. It's two entirely different processes wearing the same word, mixing, and that shared word is doing a lot of quiet, misleading work. Let's take the light version first, since we just finished talking about screens, and it follows naturally. This is called additive mixing, and the name is almost embarrassingly literal. You are adding light to light. Picture a completely dark room, the kind of total blackness where you can hold your hand an inch from your face and see nothing at all. Now imagine 3 spotlights aimed at the same spot on a white wall, one red, one green, one blue, each one dim enough on its own to leave only a soft, colored glow. Switch on only the red spotlight, and you see red, a patch of warm light sitting alone on the wall. Now bring up the green spotlight too, aiming at that same overlapping patch, and something happens that feels almost like a magic trick the first time you see it performed live, rather than just read about. The overlap where red and green light land together does not become some muddy, brownish smear, the way you might expect if you were thinking in terms of paint. It becomes yellow,
Bright, clean yellow, built entirely out of red light and green light, landing on the same spot at the same time, with no yellow light involved anywhere in the process. Bring up the blue spotlight as well, overlapping all three in the center, and that central patch turns white, or very close to it. Red, green, and blue, added together in roughly equal measure, reconstruct something the eye reads as colorless, ordinary, daylight-toned white. This is not a parlor trick specific to theatrical spotlights. It is the exact principle sitting inside every screen you have ever looked at. The same principle mentioned a moment ago with those glowing subpixels of red, green, and blue light. When a screen wants to show you yellow, it very often is not emitting yellow light directly at all. It is switching on tiny red and green elements side by side, so close together that your eye cannot resolve them as separate points, and letting your visual system perform the same additive mixing that the overlapping stage lights performed on that wall. Your eye takes in a mixture of red and green wavelengths, arriving from what is actually two different physical sources, and reports back, with total confidence, a single unified sensation of yellow. This was worked out with remarkable clarity in the 19th century, well before anyone had built an electronic display, by scientists including James Clerk Maxwell, who demonstrated as early as the 1850s that three carefully chosen colored lights, mixed in the right proportions, could reproduce the appearance of nearly any other color the eye can perceive. Maxwell's experiments with spinning color discs and projected lights laid much of the groundwork for a theory of color vision based on three types of receptors in the eye, a theory we'll sit with more directly in a little while, but which is worth simply noting now, quietly, as a thread we've already begun pulling on. So that's additive mixing. Light plus light equals more light, and specific combinations of wavelengths get reinterpreted by the eye as entirely different hues, hues that were never actually present as single wavelengths in the mixture at all. Paint works by an almost opposite logic, called subtractive mixing, and the name here is just as literal, though what's being subtracted is not obvious until you slow down and picture it. A tube of blue paint looks blue for the reason discussed earlier in this drift. The pigment inside it absorbs most wavelengths of light that strike it and reflects mainly the blue ones back toward your eye. A tube of yellow paint absorbs different wavelengths and reflects mainly the yellow ones. Now stir the two together on a palette. You are not adding light to light anymore. You are combining two different sets of light thieves into one physical mixture, and asking that mixture to sit under a single beam of ordinary white light, which itself already contains a broad spread of wavelengths, roughly all the colors at once, before anything touches it. The blue pigment particles in the mixture absorb the long reddish wavelengths, as they always did. The yellow pigment particles absorb the short bluish wavelengths, as they always did. What's left over, after both sets of pigment have each subtracted their own share from that same beam of white light, is a narrow middle band of wavelengths that neither pigment wanted, and that middle band reads to the eye as green. Green paint, in other words, isn't usually green, because it contains some special green ingredient. It's often green because two other colors of paint have each removed different pieces of the light spectrum, leaving behind whatever survived both rounds of subtraction. Mix in a third or fourth pigment, each one absorbing its own greedy share, and eventually there is nothing much left to reflect at all. That's why mixing many paint colors together tends to drift toward a dull brown, or a muddy near black, rather than toward white, the way mixing colored lights does.
Every added pigment is another layer of subtraction, another set of wavelengths removed from the pool, until almost nothing survives the gauntlet to reach your eye. This same subtractive logic, extended and refined, is what sits inside a color inkjet printer, quietly doing its work every time someone prints out a photograph or a boarding pass. Printers typically use four inks: cyan, magenta, yellow, and black, often abbreviated with the letters C, M, Y, and K, that last letter standing in for black partly to avoid confusion with blue. Cyan ink absorbs red light and reflects blue and green. Magenta ink absorbs green light and reflects red and blue. Yellow ink absorbs blue light and reflects red and green. Yellow ink absorbs blue light and reflects red and green. Yellow ink absorbs blue light and reflects red and green. By printing tiny overlapping dots of these three inks in different combinations and densities, so fine that your eye blends them together into a single perceived patch of color rather than seeing individual dots, a printer can subtract its way down to almost any hue, layering absorption upon absorption, the way stacked pigments do on a palette. Black ink is added separately mostly for practical reasons, since mixing all three colored inks together to produce a true rich black uses more ink, dries less cleanly, and tends to look muddier than a dedicated black ink handles on its own. So now there are two entirely different mixing systems, living side by side in the ordinary world, both commonly just called mixing colors, and they behave almost like mirror opposites. Add light to light, and you move toward white. Add pigment to pigment, subtracting more of the spectrum each time, and you move toward black. A screen showing you a photograph of a printed page is performing additive mixing to simulate the appearance of something that was itself created through subtractive mixing, two opposite physical processes, one nested inside a description of the other, and your visual system glides across that boundary without a flicker of hesitation, without any sense that anything strange has just occurred. Which leads gently toward one of the more genuinely disorienting ideas in the entire subject of color, something worth sitting with, slowly, rather than rushing past. Because light can be built up out of different combinations of wavelengths that nonetheless strike the eye as identical, it becomes entirely possible for two objects, or two lights, or two mixtures that are physically nothing alike to look like precisely the same color under a given set of conditions. These are called metamers, from Greek roots meaning something like beyond parts, and they are not some rare laboratory curiosity. They are woven into daily life more thoroughly than most people ever notice. A shirt and a jacket, bought at different stores, made with completely different dyes, can appear to be exactly the same shade of navy blue under the fluorescent lights of the shop, and then, carried outside into daylight, quietly reveal themselves to be subtly, unmistakably different, one leaning slightly toward purple, the other slightly toward gray. Nothing about either garment changed in that walk from the shop to the sidewalk. What changed was the light doing the illuminating, and because the two dyes had been reflecting different, mismatched sets of wavelengths that only happened to average out to the same result under one particular kind of lighting, that fragile agreement broke apart the moment the lighting itself changed. Let your eyes rest, if they haven't already, somewhere soft and unfocused, because what comes next asks something a little different of them, an experiment you can try later, half asleep, or simply imagine happening. Either way works fine. Find a small square of bright red paper, or picture one, a red about the size of a playing card, and stare at its center for perhaps 20 or 30 seconds, longer than feels natural, resisting the urge to let your eyes wander. Then look away, toward a blank white wall or a plain sheet of paper, and wait. What appears there, ghostly and uninvited, is a square of pale green, hovering for a few seconds before it softly dissolves. This is called a negative afterimage, and it has been noticed and puzzled over for a very long time, long before anyone understood the mechanism behind it. Goethe wrote about these lingering ghost colors in his own color studies in the early 1800s, fascinated by the way the eye seemed to answer one color with its opposite, though his explanation for why this happened was, in most respects, quite different from the one that modern vision science eventually settled on. The explanation that researchers arrived at later has to do with fatigue, though fatigue is really just a convenient word for something more specific happening inside the retina. Remember from earlier that color vision depends on 3 types of cone cells, each tuned to respond most strongly to a different range of wavelengths, and that the brain compares their relative outputs to arrive at a sensation of hue. When you stare at that red square for half a minute, the cones most responsive to red-associated wavelengths are working hard, signaling steadily, and steady overwork causes a kind of temporary depletion, a lessening of their responsiveness, not unlike how a muscle held in a tensed position for too long starts to lose some of its usual strength. When you then shift your gaze to a neutral white surface, which is, after all, reflecting a fairly even mixture of all wavelengths at once, the tired red responsive cones answer weakly, while the fresher cones, the ones tuned toward green, answer at their normal strength. The brain, comparing these now unbalanced signals the same way it always compares them, interprets the imbalance as color, and what it produces, briefly, is green. Nothing green is actually present anywhere in the room. The green exists only as a kind of echo of imbalance, a signature of recent history written temporarily into the responsiveness of your own retina. There is something worth pausing on here, gently, because it touches one of the recurring themes of this whole subject, the astonishing degree to which color is not simply a report of what is out there, but a record of process, of comparison, of what came immediately before. The afterimage is not an illusion in the sense of being a mistake or a trick. It is your visual system doing exactly what it always does, comparing relative cone responses, only now working from a temporarily lopsided starting point that it has no way of knowing is lopsided. From the inside, from where you are looking out, through your own eyes, there is no difference at all between color arising from present wavelengths and color arising from this kind of recent fatigue. Both simply appear as color, seamlessly, with no little flag attached explaining which is which. A closely related phenomenon, sitting quietly alongside afterimages, is called simultaneous contrast, and it shows something almost the opposite point, that color perception depends not on history exactly, but on neighbors, on whatever happens to be sitting right beside a color at this very moment. Picture 2 small gray squares, identical in every measurable way, made of the same ink, reflecting precisely the same wavelengths back to your eye. Now imagine one of them placed on a large black background and the other placed on a large white background. Looking at them side by side, the gray square sitting on black will appear noticeably lighter than the gray square sitting on white, even though nothing about either gray square has changed, even though a measuring instrument would report back the exact same numbers for both. Your visual system, it turns out, is far less interested in absolute brightness than most people assume, and far more interested in relative brightness, in how a patch of light compares to whatever surrounds it. This makes a certain kind of sense once you consider what vision actually needs to accomplish out in the world. A patch of snow sitting in the shade of a tree, and that same patch of snow sitting in direct noon sunlight, might reflect wildly different, total amounts of light back to the eye, and yet you need to recognize both as the same white snow, the same object, unchanged. A visual system that reported only absolute brightness would be constantly fooled by shifting light, would see the world redecorating itself every time a cloud passed overhead. A visual system tuned instead to relative brightness, to contrast against immediate surroundings, manages to hold on to a stable sense of what things are, despite all that constant flickering of the light falling on them. The gray square illusion, in other words, is something like the visible cost of an otherwise very useful strategy, a strategy built for consistency that occasionally produces a small, harmless miscalculation when placed in an artificially controlled setting. The same logic extends to hue and not just brightness, and this is where the effect becomes even stranger to sit with. A patch of neutral gray, placed on a red background, will often take on a faint greenish cast, drifting away from the red that surrounds it, almost as though the eye is trying to push the gray toward whatever color is missing from its neighborhood. Place that same neutral gray on a green background instead, and it drifts subtly toward pink or red. This pairing, red answered by green, is not a coincidence, and it connects back to something mentioned earlier regarding how human color vision seems to be organized around opposing pairs, red against green, blue against yellow, black against white, a system sometimes called opponent processing. The theory, associated with the German physiologist Ewald Hering, working in the late 1800s, proposed that certain neurons in the visual pathway are wired to increase their firing rate in response to one member of a pair and decrease it in response to the other, so that red and green are, in a very real neural sense, pulling against a shared seesaw rather than existing as entirely independent channels. This idea sat in tension with the earlier three-color theory associated with Young and Helmholtz for a long time, each side of the debate accumulating evidence, until researchers eventually came to understand that both were capturing something true, just at different stages of the visual process. The three cone types Young and Helmholtz described really do exist at the very first stage, out in the retina, but their signals are then recombined further along the pathway into exactly the kind of opposing pairs Hering had proposed, red against green, blue against yellow. Afterimages and simultaneous contrast, as it happens, are among the most direct pieces of evidence for this opponent organization, since they show, so plainly, colors behaving as if pulled toward whatever sits opposite them on this internal seesaw. None of this means color is arbitrary, or that your visual system is simply unreliable, prone to error in some careless way, and it is worth being careful here, because it would be easy to walk away from these illusions with an exaggerated sense that vision is untrustworthy or broken. What these effects actually reveal is closer to the opposite, a system so committed to extracting stable, useful information about a genuinely unstable, shifting world that it deliberately discounts certain kinds of raw data in order to hold on to something more valuable, namely constancy, the recognition that this is still the same object, the same shirt, the same wall, even as the light bathing it drifts and changes from one moment to the next. The gray square did not become a different color. Your eye simply refused,
quietly and automatically, to be fooled by its background, and in refusing, produced a small and rather beautiful distortion of its own. One more thread in the long, patient story of how the brain builds something called color out of raw light. Memory, comparison, and context, layered so seamlessly together that none of the layers ever announce themselves individually, and it is to that layering and to how it plays out across an entire visual scene rather than a single square that the next part of this story will slowly turn.
Long before anyone tried to measure color, people tried to sort it, and the sorting itself tells you something about how strange and slippery the whole subject has always been. Ancient Egyptian painters worked with a small, fiercely guarded palette, ochres dug from the earth, a blue made from ground copper and sand fired at just the right temperature, a green from malachite, and they organized these not by any abstract theory, but by where the pigments came from and what they could afford to buy or trade. Color, for most of human history, was a material fact before it was ever an idea. It lived in the mineral, the insect, the shellfish. The purple that later draped Roman emperors came from a small sea snail, and it took thousands of crushed shells to dye a single garment, which is part of why that particular hue became so tightly bound up with power and rank. To ask what purple truly was would have seemed like an odd question. Purple was that dye, from that snail, at that price. The first real attempt to impose an intellectual order onto color, rather than a commercial or ritual one, came from Aristotle, who proposed that all colors arose from mixtures of light and darkness, arranged in a line running from white down to black, with the familiar hues stacked in between, like rungs on a ladder. It was a tidy picture, and a wrong one, in ways that would take many centuries to fully untangle, but it held enormous authority, partly because so few people had any competing framework to set against it, and partly because it fit neatly with a broader belief that color was fundamentally a modification of light and dark, rather than something with its own independent structure. For close to 2,000 years, this linear view, with occasional variations, was simply what educated people assumed color to be. Then, in the late 1660s, a young and famously prickly Isaac Newton shut himself in a darkened room in Cambridge, drilled a small hole in his shutter to let in a single beam of sunlight, and passed that beam through a glass prism. The light spread out into a familiar band of hues, red through violet, which was not itself a new observation, since prisms had produced this effect for craftsmen and natural philosophers before him. What Newton did next was the crucial step. He took a second prism and passed the separated colors through it again, and rather than the color continuing to change or blend into something new, each individual hue passed through unaltered, refracting at its own fixed angle. This told him something Aristotle's model could never have predicted, that white light was not pure and simple after all, but a mixture, and that the prism was not adding color to the light, so much as sorting a mixture that had been hiding there all along. Newton went on to arrange these hues into a circle, a color wheel, with red and violet meeting at one seam, and he chose 7 named bands: red, orange, yellow, green, blue, indigo, violet, partly for reasons of careful observation, and partly, by his own admission, because 7 carried a kind of numerological weight for him, echoing the 7 notes of a musical scale. It is a small, human detail, worth sitting with for a moment, that one of the foundational documents of modern color science contains a division shaped in part
by an aesthetic preference for a particular number.
Newton's wheel measured something real, the physical composition of light, but it was silent on a great deal else, including why mixing colored light behaves so differently from mixing colored paint, a confusion that would linger and cause trouble for a long time afterward. It also had nothing to say about the experience of color, the simple fact that a hue looks different in a garden at noon than it does under a candle at midnight, a silence that would eventually draw a very different kind of thinker into the conversation. That thinker was Johann Wolfgang von Goethe, better known now for his poetry and his novels than for his science, though he considered his work on color among his proudest achievements, prouder, he sometimes said, than his literary output. Goethe found Newton's account cold and incomplete, too willing to treat color purely as a matter of measurable wavelengths, while ignoring the living experience of actually seeing it, the way a red can feel warm and advancing while a blue feels cool and receding, the way colors shift and interact depending on what surrounds them, on the observer's mood, on the quality of the light in the room. He spent years conducting his own experiments, using prisms in ways Newton had not, and while some of his physical claims did not hold up, his instinct that color is never purely a property of light striking a surface, that it always involves a perceiving mind actively shaping what arrives, turned out to be more prescient than his contemporaries gave him credit for. Goethe was, in a sense, describing the very phenomena that would later be called color constancy and simultaneous contrast, long before anyone had the vocabulary to explain why they happened. He was measuring the wrong things by Newton's standards, and yet noticing something true that Newton's own framework had no room for. For much of the 19th century, these two lineages, the physical and the perceptual, ran along somewhat separate tracks, until Thomas Young, an English polymath who also helped decipher the Rosetta Stone in his spare time, proposed in the early 1800s that the eye did not need a separate receptor for every possible hue, an idea that had seemed almost necessary given how many colors people could distinguish. Instead, Young suggested three types of receptors, tuned broadly to different parts of the spectrum, whose combined signals could account for the full range of human color vision through mixture alone. It was a strikingly economical idea, and it sat largely unproven for decades, until Hermann von Helmholtz, a German physicist and physiologist with an almost restless breadth of interests, spanning acoustics, optics, and the physiology of nerves, took up the theory, refined its mathematics, and tied it much more securely to actual experimental measurements of how people match and mix colored lights. Together, their names became attached to what is still called trichromatic theory, and it explained, with real precision, why mixing three well-chosen colored lights can reproduce an enormous range of visible hues, a principle that, without anyone in the room fully realizing it yet, would eventually become the operating logic behind every television and every glowing screen. Around the same period, James Clerk Maxwell, a Scottish physicist whose other work would go on to unify electricity, magnetism, and light itself into a single elegant theory, turned his attention to color as a more hands-on, almost playful problem. In 1861, he arranged for the projection of what is often called the first color photograph, taken by photographing a tartan ribbon 3 separate times through red, green, and blue filters, and then projecting all 3 images back together, superimposed, onto a single screen. The result, imperfect and technically lucky in ways Maxwell himself may not have fully appreciated, was nonetheless a working demonstration that 3 channels of light, properly combined,
could reconstruct something resembling the full colored world. He also devised a spinning color wheel, dividing a disk into precise wedges of different hues, which when rotated quickly enough, would blur together into new, blended colors before the eye, letting him quantify color mixture with a rigor that earlier observers, working mostly by comparison and description, had never quite managed. What these figures were collectively building, across more than 2 centuries and without any single shared plan, was less a final answer than a widening set of partial maps, each one accurate within its own borders, and each one blind to whatever lay just beyond them. Newton mapped the physics of light splitting apart and recombining. Goethe mapped the felt, contextual, embodied experience of seeing color, however unevenly reasoned his conclusions sometimes were. Young and Helmholtz mapped the receptors in the eye, while Maxwell showed how their outputs could be reproduced and manipulated mechanically, on paper discs and glass plates alike.
None of these maps contradicted the others so much as they measured entirely different layers of the same eventual mystery, and it would take the arrival of formal color spaces, precise mathematical systems for pinning down and comparing every visible hue, to begin drawing all these separate layers onto something resembling a single shared chart. Let's slow down for a moment and turn the question sideways, because everything said so far about red and green and blue has quietly assumed a particular kind of eye, the ordinary human kind, 3 cone types, 1 narrow window of wavelengths, and that assumption, so easy to forget precisely because it feels so natural, is itself one of the strangest things about color once you notice it. Start with what happens when that ordinary arrangement doesn't quite hold, even within our own species. Most people carry 3 types of cone cells, each tuned, roughly, to long, medium, and short wavelengths, and the brain compares the relative firing of these 3 populations to produce the sensation of hue. But roughly 1 in 12 men, and a much smaller fraction of women, have a version of the gene for the long or medium wavelength cone that shifts its sensitivity, sometimes only slightly, sometimes so far that 2 cone types end up almost overlapping, instead of comparing usefully different signals. This is what gets called color blindness, though the phrase is misleading in a way worth sitting with. Most people with this condition are not seeing a gray, drained world. They are seeing color, plenty of it, just with fewer reliably distinguishable categories, so that certain reds and greens, which to a trichromatic eye look obviously different, collapse toward each other, becoming harder or impossible to tell apart by hue alone. A red apple and a green leaf might still differ in brightness, in texture, in every cue except the one most of us lean on without thinking, and the person is very often navigating the world using those other cues so smoothly that the difference goes unnoticed for years, sometimes for a whole childhood, until a colored diagram in a classroom or a strand of Christmas lights gives it away. There is an old story, not entirely reliable in its details but useful anyway, about the chemist John Dalton, who in the late 18th century became so puzzled by his own inability to distinguish certain colors, particularly the pink of a geranium flower, which looked to him almost exactly like its green leaves, that he wrote up his observations and had them read to the Manchester Literary and Philosophical Society in 1794, making his own vision, quite deliberately, into a scientific case study. He guessed, incorrectly as it turned out, that the fluid inside his eyes was tinted blue, filtering out certain wavelengths before they ever reached his retina, and he asked that his eyes be examined after his death to test the idea. They were,
and the blue fluid theory did not hold up. But the underlying condition he described so carefully still sometimes carries his name, and his willingness to treat his own private perceptual world as data worth reporting, rather than an embarrassment to hide, was itself a small, quiet act of scientific courage.
Now push in the other direction, not toward fewer functioning cone types, but toward more, because a small number of women, thanks to a particular genetic circumstance involving the X chromosome, on which the genes for the long and medium wavelength cones happen to sit, may carry 4 distinct cone types instead of 3. This happens because women have 2 X chromosomes, and if one of those chromosomes carries a slightly mutated version of the long or medium wavelength cone gene, a woman can end up expressing the ordinary version on one X chromosome and the shifted version on the other, giving her, potentially, 4 differently tuned cone populations working at once instead of the usual 3. This condition is sometimes called tetrachromacy, and it has attracted a great deal of popular fascination. Magazine articles describing women who can supposedly see 100 million colors compared to the mere million available to everyone else. The reality, as researchers studying it have found, is considerably more cautious and more interesting. Simply having the extra cone type is not enough. The brain also has to be able to make functional use of the additional channel of information, extracting from it distinctions that a standard 3-cone system cannot make, and testing for this turns out to be genuinely difficult, because you need color differences fine enough that only a 4th channel could resolve them, and you need a subject whose visual system has actually learned to use that channel in a discriminating way, rather than simply carrying the extra hardware without fully exploiting it. Some studies have found women who do seem to make behaviorally meaningful use of a 4th cone type, distinguishing color pairs that trichromatic observers cannot tell apart, while other potential tetrachromats, despite having the right genetics, show no measurable advantage at all. The honest, current position is that functional tetrachromacy in humans appears to be real in at least some cases, but rare, subtle, and still being carefully mapped, not a hidden superpower waiting undiscovered in a large fraction of the population. And even this expanded picture is still narrow compared to what other animals routinely do. Many insects, and a good number of birds, can detect ultraviolet light, wavelengths shorter than violet, which lie entirely outside what a human eye can register at all, no matter how well rested or attentive the viewer. Bees, famously, see patterns on flower petals that are functionally invisible to us, ultraviolet markings, sometimes called nectar guides, faint radiating lines, or contrasting patches that lead a bee's eye, so to speak, toward the flower's center, the way a runway's lights lead a plane toward a landing strip. To a human, standing in a garden, the flower might look like a uniform sheet of yellow. To a bee, it is patterned, structured, practically labeled. Birds, for their part, often possess a 4th cone type sensitive to ultraviolet or near ultraviolet light, which, among other things, means that some birds, whose plumage looks plain or uniformly colored to human eyes, may actually display elaborate ultraviolet patterns to each other, differences in mate quality or individual identity that are, quite literally, written in a part of the light spectrum we cannot read. Other animals extend the picture in a different direction entirely, not by adding wavelengths, but by adding a whole different property of light most people never think about at all, called polarization. Ordinary light, even though it travels as a wave, vibrates in many directions at once as it moves, but light can become polarized, meaning its vibrations become aligned along a particular plane, and this happens constantly in nature, for instance when sunlight scatters off the sky or reflects off water.
Human eyes are almost entirely insensitive to this property. Polarized and unpolarized light of the same color look identical to us, but many insects and cephalopods such as octopuses and cuttlefish can detect the plane of polarization directly, and for some of them, this functions almost like an entirely separate sensory channel layered on top of ordinary color vision. Letting a mantis shrimp, to take one of the most extreme examples in the animal kingdom, read patterns in reflected light that to a human observer would be perfectly invisible, a hidden layer of the visual world sitting right on top of the one we already know, unnoticed simply because we lack the equipment to notice it. All of which brings us to something worth sitting with quietly for a moment before moving on. It is tempting, hearing about a bee's ultraviolet flower markings or a mantis shrimp's polarization vision, to imagine what it would be like to borrow those eyes for an afternoon, to see the extra colors, the hidden patterns, the invisible light made suddenly visible. But this imagining runs into a wall that turns out to be more interesting than the fantasy itself. A human brain, wired from birth around 3 cone types and their particular pattern of comparisons, has no ready-made place to put a 4th or 5th channel of raw color information, even if you could somehow pipe that information in.
Color, as earlier sections of this account have tried to show, is not simply a matter of receiving a signal. It is a matter of a whole nervous system having been shaped, over a lifetime and over an evolutionary history, to interpret that signal in a particular structured way. Borrowing another creature's photoreceptors would not automatically grant you their color experience, because their experience depends just as much on everything downstream of the eye as it does on the eye itself, a whole different architecture of comparison and interpretation that no human brain currently has, and this gap between what a receptor can detect and what an entire nervous system knows how to do with the detection turns out to be exactly where the next layer of this story is waiting. Now let's turn to something that happens entirely downstream of the eye, in territory that has nothing to do with cones or opsons or wavelengths at all, and everything to do with a much stranger question. What happens to color once it meets language? Start with a small, well-documented puzzle that has quietly unsettled a lot of people who first encounter it. Ancient Greek writers, describing the sea, sometimes called it wine-colored, and Homer's descriptions of color in general, when scholars have gone through them carefully, are unusual by modern expectations. The sky is rarely called blue. Certain words that seem to modern readers like they should map onto blue or green get used in ways that don't quite line up with contemporary color categories. This observation, made in the 19th century and revisited many times since, once led to some fairly wild speculation, including a period where a few researchers wondered whether ancient people might have been physically unable to see blue, as though color blindness itself had a history. That particular idea has not held up. There is no good evidence that human eyes have changed in any meaningful way over the few thousand years in question, and no reason to think a Greek sailor's retina processed the sky any differently than yours does tonight. What was different was not the seeing. What was different was the sorting, the naming, the set of categories a language offered its speakers for carving up the same continuous rainbow that everyone's eyes have always presented to everyone's brain. This distinction matters enormously and is worth holding gently in mind. The raw sensory experience, as far as anyone can tell, was almost certainly there the whole time. What varies, across history and across languages spoken right now, is which parts of that experience get bundled together under a single word and which parts get split apart. Many languages, studied across a wide range of unrelated cultures, developed color vocabularies in a surprisingly consistent rough order. Words for black and white, or more precisely, for dark and light, tend to come first. Red tends to follow. Then, in various orders, depending on the language, yellow and green, with blue reliably arriving late in the sequence almost everywhere it has been studied. Blue, it turns out, is oddly rare in nature as a pigment, rarer than it looks, since most of what reads as blue in the natural world, from butterfly wings to blue jays to that Greek sky, is not pigment at all, but structural color, the same kind of light-bending trick discussed earlier in this account, and rare pigments tend to produce late or absent color words. A language can go a very long time without ever needing a single word that separates blue from green, lumping both under one broader term, not because its speakers cannot see the difference, but because their culture never needed to talk about that difference often enough for a dedicated word to take root. And here is where the story gets genuinely more delicate, because there is real, ongoing, careful research suggesting that language does not just describe color after the fact, but can lean on how quickly and how easily a person notices or remembers certain color differences. Studies using groups whose languages split blue into two distinct basic terms, one for lighter blue and one for darker blue, a division English does not make, have found small but measurable advantages in how fast those speakers can pick out the boundary between the two shades in a quick visual search task, faster, on average, than speakers of a language treating the whole range as one blue. Other work has found that briefly loading a person's verbal working memory, having them silently repeat a string of nonsense syllables while performing a color categorization task, can shrink or even erase certain language-linked advantages, suggesting that at least part of what is being measured is a fast, semi-automatic naming process running quietly in the background of a visual task, nudging judgment just slightly rather than any difference in what the eye physically registers. This has become one of the more carefully contested corners of color science, and honest researchers describe it that way, as contested rather than as a settled verdict on whether language shapes perception. The responsible summary, the one that respects both the data and its limits, is something like this. Color language does not appear to change what the eye detects or paint new hues into a person's visual field, but it may, in some measurable circumstances, change how quickly certain distinctions get noticed, sorted, or held in mind, a subtle thumb on the scale rather than a different picture altogether. Memory offers its own quiet complications, separate from language, but tangled up with it. If you ask someone to recall the color of a shirt they saw briefly an hour ago, what they report back is not a faithful photographic readout, it is a reconstruction, and reconstructions lean on categories. People tend to remember colors as slightly closer to the best, most typical example of whatever category they mentally filed the color under, a phenomenon sometimes called categorical drift. A cup that was actually a slightly greenish blue gets remembered later as a little more purely blue than it really was, nudged toward the category's prototype, the way a slightly off note played on a piano still gets heard, in memory, as the note it was closest to. This is not a flaw exactly, more a byproduct of how memory in general works, compressing continuous experience into something more categorical and storable, and it happens with color the same way it happens with the remembered shape of a face or the remembered layout of a room, details softening toward familiar templates the longer they sit unused.
Emotion attaches to color in ways that are partly universal and partly stubbornly local, and separating the two threads takes some care. There is reasonably consistent evidence, gathered across a range of cultures, that red tends to draw faster attention and gets associated, more often than not, with arousal, urgency, warmth, sometimes danger, sometimes desire, a pattern plausible enough given red's long association with blood, fire, and ripening fruit, that some researchers suspect a biological thread running underneath the cultural one. But plenty of color-emotion associations refuse to generalize so neatly. White, worn at funerals across parts of East Asia, worn at weddings across much of the West, cannot be explained by wavelength or by shared biology, only by history, by centuries of accumulated custom settling like sediment onto a particular hue until the color itself seems, to someone inside that culture, to simply mean what it means, obviously, inarguably, the way water simply means wet. Art history offers a slower, more visible record of this same layering process. Blue pigments, for most of human history, were genuinely difficult and expensive to produce. Ultramarine, in particular ground from lapis lazuli, mined almost exclusively in a single remote region of what is now Afghanistan, shipped across enormous distances, priced at points in history on par with gold by weight. Painters used it sparingly, reserved it for their most important subjects, the robes of the Virgin Mary in countless medieval and Renaissance paintings, a color deliberately chosen not just for its visual coolness, but because its very costliness was itself a kind of statement, wealth and devotion painted directly onto the canvas. It took the accidental discovery of a synthetic alternative in the early 18th century, a pigment now called Prussian blue, made by a color maker in Berlin, who was reportedly trying to produce something else entirely and stumbled onto a rich, stable blue instead, to loosen blue's grip as a luxury color and put it, slowly, within reach of ordinary painters, and eventually ordinary walls and ordinary clothing.
None of this changed a single cone cell in a single human retina. It changed what colors were affordable to make, which changed what colors got used, which changed what colors came to feel, generation after generation, symbolically loaded, culturally weighted, quietly meaningful, in a way that has nothing to do with the physics of light and everything to do with the accidents of mining, trade routes, and one dissatisfied German color maker's failed experiment. So the picture that emerges from all of this is neither the simple claim that language and culture invent color out of nothing, nor the opposite claim that naming and meaning are irrelevant decoration sitting on top of a purely mechanical visual process. It is something quieter and harder to summarize in a single sentence, a layered system in which raw detection happens early and mostly independent of what any given culture calls it, while categorization, memory, meaning, and use all continue building on top of that raw material for as long as a person lives inside a particular language and a particular set of customs, each layer shaping the next just slightly, the way sediment shapes the riverbed that will guide the next year's water. And having spent this much time on how outside forces, language, culture, memory, shape a shared human experience of color, it is worth turning next to something even more private, the question of whether two people, standing side by side and looking at the very same red apple under the very same light, can ever really know if they are having the same experience at all. Let's sit with that question for a moment. Not to solve it, because it cannot really be solved, but to feel the shape of it, because the shape of it is calming in its own strange way. Two people stand in front of the same apple. The same photons are bouncing off its skin, the same wavelengths reaching two sets of eyes. the same rough population of long and medium cone cells firing in something like the same pattern, and yet there is no way, none at all, to climb inside another person's head and check whether the private feeling of redness, the actual felt quality of it, matches your own. You can ask them to name the color, and they will say red, and you will agree. But agreeing on the word proves only that you both learned English the same way, not that the inner experience is identical. This is sometimes called the problem of qualia, a word philosophers use for the raw felt quality of an experience, the redness of red as it is lived rather than as it is measured, and it has been debated for centuries without arriving anywhere close to a settled answer. Some thinkers have argued the question is meaningless, that asking whether your red matches my red is like asking whether your inch is the same length as my inch, when there is no ruler that can measure a feeling. Others have argued that even if we can never prove it, there is still a fact of the matter, some truth about the comparison that simply sits forever out of reach. Both positions have serious defenders, and neither has won, and you do not need to pick a side tonight. It is enough to notice that this question exists at all, quietly, underneath every ordinary conversation about color. Every time someone says that shirt is such a nice blue, and everyone nods, each person nodding from inside a completely sealed and private theater that no one else will ever get to watch. But here is something gentler to hold alongside that unanswerable question, which is that the very fact you cannot prove your red matches anyone else's does not mean color is arbitrary or meaningless or purely invented. It means color is relational, all the way down, at every level we have walked through together. It begins with light, an ordinary physical thing, waves of energy, radiating outward from the sun, or a candle, or a lamp, indifferent to any eye, carrying no color of its own, only frequencies, and lengths, and energies, a description that would be complete and correct, even in a universe with no living creature anywhere to see it. Then light meets a surface, an apple skin, a square of cloth, a slab of stone, and the surface does something particular to that light, absorbing some wavelengths into itself as tiny vibrations of heat, and sending others, bouncing back out into the world, and which wavelengths it keeps and which it reflects depends on the surface's own molecular structure. The arrangement of pigments, or the microscopic architecture of feathers or wings that can bend light through interference rather than pigment at all, so that even here, before any eye is involved, the world is already sorting light in complicated and specific ways. Then that reflected light finds its way to an eye, a genuinely strange and improvised organ, evolved not to reveal truth, but to help some ancient ancestor find ripe fruit, or a mate's flushed skin, or a predator half hidden in leaves. An organ built from 3, sometimes 2, sometimes 4 types of light-sensitive cells, each tuned to overlapping bands of wavelength, so that color, as your body first registers it, is not a direct reading of the world, but a compressed summary, a rough sketch, made from only a handful of measurements, the visual equivalent of judging a whole orchestra by the loudness of 3 separate microphones. Then that rough sketch travels inward, through a nerve, into a brain that immediately begins editing it before you are ever aware anything happened, correcting for the color of the ambient light, so a white shirt still looks roughly white under orange lamplight or blue morning sky, filling in colors your peripheral vision barely registers, smoothing shadows, comparing patches of the visual field against each other rather than measuring any patch in isolation,
so that what finally arrives in your conscious awareness has already been shaped, adjusted, and interpreted many times over by machinery you have no direct access to and no memory of running. And then, on top of all of that, comes language and culture, the words a particular community happen to settle on, the boundaries different languages draw in different places along the same continuous rainbow, the extra words some languages carry for shades that other languages fold into a single term, and the centuries of accident, which pigments were rare and which were common, which dyes could survive a boat trip across an ocean, and which could not, which colors ended up on the robes of the powerful, simply because no one else could afford them, all of it settling slowly into habits of meaning that feel timeless and natural, but are really just sediment, laid down over generations, shaping what a color comes to mean to the people who grow up surrounded by it.
So when you ask, quite reasonably, what color actually is, the honest answer is that it is not one thing sitting in one place waiting to be found. It is not simply in the light, because the light itself carries no color, only physical measurements that a color word gets attached to afterward. It is not simply in the object, because the same tomato can look muted and gray in near darkness, and vivid and red in full sun, the object itself never changing at all. It is not simply in the eye, because two healthy eyes with typical cone cells can still end up, after all the brain's correcting and comparing, reporting mildly different experiences of the exact same scene, as anyone who has argued with a friend over whether a photograph is more blue or more gold already knows firsthand. And it is not simply in the mind either, floating free of anything physical, because if you close your eyes, or step into true darkness, the sensation reliably disappears, which is not what you would expect from something invented purely inside your head with no outside anchor at all. Color turns out to live in the relationship between all of these things at once: light, surface, eye, brain, memory, language, and the specific surrounding context in a given moment, a genuine collaboration between a world that has real physical properties, whether or not anyone is looking, and a nervous system built by a long, slow, accidental history of survival, rather than by any impulse toward truth, and a mind further shaped by a particular culture's particular habits of naming and caring about certain distinctions, and letting others blur together. Take any one of those pieces away, and color, as you actually experience it, stops existing in quite the same form. Take away the light, and there is nothing to see at all. Take away the surface, and there is nothing for light to bounce from. Take away the eye, and the light passes through empty space, unregistered by anyone. Take away the brain's constant correcting, and the world would flicker and shift in ways that would make ordinary seeing almost unusable. And take away language and culture, and you would likely still see, in some rough sense, but the tidy business of naming, comparing, remembering, and caring about this particular color, rather than that one, would loosen and blur into something far less structured than what you carry around, without ever noticing the structure at all. There is something quietly comforting in this, more comforting perhaps, than either of the two simpler stories would have been. It would have been comforting in one way, to learn that color is simply a fixed property of the world, sitting there in objects waiting to be read off correctly or incorrectly. It would have been comforting in a different way, to learn that color is entirely a human invention, ours alone to define however we like. But the truth sitting in between those two stories is its own kind of comfort, because it means your experience of color, right now, in whatever room you are lying in, is neither an illusion layered over nothing real, nor a passive reading of some fixed external fact. It is a genuine event, happening freshly each time, built from real photons that traveled real distances, met a real surface with a real molecular structure, entered a real and ancient piece of biological machinery in your eye,
and arrived in a mind that has spent an entire lifetime, since before you could speak, quietly learning what to call it, and what to feel about it. Every time you notice color, even in the last dim moments before sleep, some far corner of the room holding on to its color more by memory than by light, you are taking part in something that took billions of years of stars fusing elements and forming light, and millions of years of eyes evolving in oceans and forests, and thousands of years of humans mining stone and boiling insects and grinding pigment and naming shades, all arriving together in this one unremarkable, quiet, completely ordinary moment of simply looking, or almost looking, at the world around you. You do not need to hold on to any of it. You do not need to remember the tone cells or the pigments or the Berlin color maker or the unanswerable question about the apple. You can simply let the colors of the room go soft now. Let the edges blur the way they already do in dim light. Let the naming and the comparing and the wondering quiet down together, and rest. Rest well.